All right. Yesterday, Mr. Ruzuru was using but 2018 version. So I think there were some lapses there because he was using 2018 version and what you have installed is 2014. So what you have to do is, so I will just probably take this off and then just rush through it so that we can understand better. Once you have gone to stratigraphy or even at home tab, you can go to folder and you take new well tops. Once the new well tops appears, you can toggle it down, you see everything that you have there. Then we are at our well section window. He took time out to explain why we have to arrange them in this order. When you display the log in a 2D window, you can see the directions in which the logs are. You can see the direction, so you have to correlate in that direction. You can just click on any of it, right click. Once you right click, you see the name of it. So TM2 is what is coming first. TMB2 is what is coming first. So it shows that our first well is TM2. So if you check all the order, then you have to now arrange them now in that particular order. That's what he explained yesterday. Okay, so once you have done that, you go to two palette. All right, you take what you have here. All right, so what he was using yesterday was 2018 version that has exactly the well correlation there, but this one does not. So you are going to take X section editing. So you take X section editing, it appears there. That's what appears there. Once you take X section editing, you come to this button. Once you click, it appears there. You don't need to click anything there. So once I click here, once I just come here, I'm correlating. I take the first one, immediately horizon one appears. It has appeared under stratigraphy. That is it under stratigraphy. So I'll correlate it like that. That's the first one. Then I may pick this one also as the first. Pick it there, pick it there, pick here, and then maybe I pick there. All right, that's horizon one. Once I come, I click the same button, you realize that they now say no active surface. It means that whatever you do, there is no surface. Even if you click, nothing will appear because there is no surface that will appear. Well, what you have to do now is once you click it again, and I'm going the second time, it is now a new surface. That's horizon two that is appearing. So I just take it like that. I take it like that. So I correlate. I have that. Then I have that. All right, so that's the first reservoirs that we have down there. So you can do it the same right up. You can do it the same from bottom to up. So I'll just come here, double click two times, and I change the name to R1 base, reservoir one base, applied and okay. Then I come here, I change it to reservoir one top, reservoir one top, reservoir one top, then applied and okay. So you can, once you correlate from bottom to top, this now, the next one now will be reservoir two. So we are through with reservoir one. We have picked the first reservoir across the entire region. So that's how you correlate from bottom to top. So what we want to do is we are supposed to do static modeling. For static modeling, we are going to do porosity modeling. We are going to do fascist modeling and net to gross modeling. But we don't have fascist and the net to gross lock yet. So we have to create it. So what I will do now is I go to well, I take calculation. On the calculation, I want to create the fascist log. So I will write there fascist is equal to what I want to use to define my fascist is the gamma ray log. That is the volume of shale from gamma ray. I can still use this gamma ray value to define my fascist, but the best one will be volume of shale. The best one is the volume of shale. That's what I'm going to use to define my fasci. So what I will do now is, when I look at the template, hold on 1 minute. Once the template is wrong, there's a problem there. When I come to volume of shale, when I look at this template here, FRA does not stand for volume of shale, so there should be a problem there. So I have to go and change that. I have to come to template and change it and look for volume of shale. I can just keep clicking V, because once that template is wrong, that's volume shale. Once that template is wrong, there is a problem. You start facing difficulties along the line. So I see that volume of shale is okay there. So I will go back to my calculator. I want to calculate the fascis. I want to determine the fascis. Fasci is equal to, if I put if, wherever this line appears, don't touch it. Just write what you want to write there. Don't shift it, because the system is already arranging in a manner. Don't shift it. So I will write volume of shale. If volume of shale is less than or equal to 0.15, is less than or equal to 0.15, I just shift it in front. You have the button on your keyboard where you have the arrow up, down, right and left. You just click the right value, it goes in front. You don't skip any space. It is just immediately after that dot. If my volume of shale is less than 0.15, the system will recognize it as 0. Then I click it again after the dot. The system will recognize it as 0. I take again if volume of shale is greater than 0.15, space, and volume of shale again is less than or equal to 0.3, the system, I take it in front after the dot, the system will recognize it as 1. So we are saying that less than less or equal to 0.15, the system recognizes as 0. Between 0.15 and less than or equal to 0.3, the system recognizes as 1. I take it again immediately after that dot. I take if again. If volume of shale is greater than, okay, that's greater than or equal to, is greater than or equal to 0.3, and volume of shale is less than 0.5, the system will recognize it as 2. Then above 0.5, I will shift it in front. Above 0.5, the system will recognize it as 3, because there is no other division again up. So above 0.5, the system is recognizing it as 3. So let's be sure here we have greater than 15 and less than or equal to 0.3. Then here we have, no, it cannot be, here will just be greater than 0.3, and volume of shale less than 0.5. The system recognizes it as 2. Otherwise, the system is recognizing it as 3. That means anything above 0.5, the system recognizes at 3. The template is going to be fascis. So I keep pressing F until I see fasci. Then from this one is just to tell you that what is going to be the interval of measurement. You can still take volume of shale. Yeah, you can still take volume of shale. There's no problem there. So where is the volume of shale? I'm seeing volume of shale 1. Okay, this is it there. All right. Once you do that, you click enter. Once you click enter, if nothing shows, it shows that the log, everything has been calculated. So I will take this off. I come now to global well. If I go down, I see my fascist log there. Once I toggle it on, I see how the fascist now will appear. So it's telling us that we have sand here, and then we have shale around this area, interlayers, and all of that. What I will do now is I will go to the setting or I will go to edit global color and see that this is exactly what 0, 1, 2, and 3 stands for. Once you identify it as Fashi, the system is seeing 0 as sand, 1 as fine sand. That's what they have defined. But we want to give our own definition. The 0 is going to be clean sand. The 0 is going to be clean sand. The 1 is going to be maybe shaly sand. It has a little bit of shale there, shaly sand, because our 1 was from 0.15 to 0.3. Then our 2 was from 0.3 to 0.5. So we'll just call it sandy shale. It's a shale that has some amount of sand in it. And then 4, we are just going to call that 4 shale. 3, we are going to call 3 shale. So we leave it like that. You can still decide to change the colors. It's your choice. You can still decide to change the colors. Whatsoever color you wish, you can still decide to change the colors. But we are going to leave it like that. We apply. And okay. So we have corrected what our 0 and 1 stands for and all of that. That is it, that is saved. So our fascis is okay. We have our fasci. We will go now to net to gross. Net to gross also, and see how we can calculate it. We have our calculation. So we could just say net to gross is equal to, if net to gross comes in when you bring porosity, water saturation, and volume of shale. That means if your reservoir is good enough to contain hydrocarbon that is exploitable, the porosity should be at least 15. That means it should be greater than 15. The volume of shale should not be more than 0.3 if our cutoff value of shale is 0.3, depending on the basin. Then your water saturation should not be more than 0.5, for example. So I will say if porosity, effective porosity, is greater than 0.15, comma, not comma, space, and volume of shale is less than or equal to anyone, there's still no problem, less than 0.3, and water saturation is less than 0.5. It should not be less than 0.5. If all of these criteria holds, the system should recognize it as 1. Otherwise, the system should recognize it as 0. So there are just two things in net to gross. Either it is recognizing it as 1 or it is recognizing it as 0. So I will come now to this template and I take net to gross. That's it there, net to gross. I'll take net to gross and I take enter. The log does not exist. So it shows that there's one log that does not exist for TMB2. There's no problem. I will continue. Okay for all. I will calculate it for, I've calculated it. That's okay. It shows up for TMB2. Probably one of these things are named differently. So I can take this maybe for TMB2. Let's look at TMB2 and see. If I toggle this log down, you see, okay, that's volume of shale is okay. Oh, so porosity is not there for TMB2. Volume of shale is there. Water saturation is not even there. Anyway, there's no problem. We cannot go back and start doing that. Remember, I said yesterday that doing petrophysical analysis with this is very, very difficult. Doing petrophysical analysis with this is very difficult. So what you have to do is you do the analysis, calculate your permeability, porosity, and permeability and porosity with volume of shale, everything with TED log. Then you export the log, then you bring it out to petrel before you do all of this. What you're going to use petrel to calculate is just your net to gross and your fascis. It's your net to gross and your fascis. So that is no problem. We'll leave it there. That's our net to gross. So what we want to do next now is to see how we want to convert because you cannot be building a reservoir if you don't have the reservoir. What they will do normally is they will use seismic to pick the reservoir. I think those of you who attended the face-to-face training in March, we showed you how you can actually pick a reservoir across a seismic, how you can actually pick a reservoir across a seismic. But what we are going to do here is I'm going to show you another method of obtaining a horizon if you don't have a seismic to pick it across. But the disadvantage of this method is if I am using these well logs to build a horizon, the horizon will just be a horizon that cuts only across this area. So we are going to have a horizon like that cuts only across, that covers this area like that in a rectangular manner, like that covers this area. That means if I want to sample a zone around this area, this particular surface is going to miss that zone because it will pick only zones like that. You build a surface only around the area where you have the wells in a rectangular manner. The surface is going to be big, but not large enough probably to cover the entire area. If you want to cover the entire area, you either pick it on seismic, or you are sure that your well you have built, they have drilled well at every point of that in that particular basin before you can pick a surface that goes across that particular basin. So what we are going to do now is we are going to build a surface. So we go to stratigraphy. We have here make surface. Under stratigraphy, we go to make surface. We click on it. Now we are going now to select which surface, what is the input. We want reservoir 1 to be as the input. We want reservoir 1 to be as the input. We are just going to call it surface 1. We are going to call it surface 1. We want to run for all main input. That means we want to run it for every horizon that we have here. You have to click this. It runs it for every horizon that you have here. Then what makes the difference now is what is your suggested settings. We are going to select what do you have as your input to build that surface. What we have is the well tops. So what we are using is well tops high density. That's what we are going to use to build that surface. Then you come to geometry and you take automatic. Then you take apply. Once you take apply and okay, you realize that these are the two that we have. Reservoir 1 top, that's the reservoir 1 top. This one is called surface 1 because I just named it surface 1. I was the one that gave the name to it. So if you look at what we have here, I gave the name to it surface 1. So this surface 1 is our R1 base. So I can still rename it. So once I go now to my 3D window, I can display the surface. Oh, the surface is not. All right, that's the surface. All right, that's the surface that we have. That's the surface that we have for the wells. That's the second surface. This is the one. Surface 1 is, let me rename it. I can say R1. My machine is freezing. Ooh, info. I can just say R1 base so that I don't get confused. R1 base so that I don't get confused. So apply and okay. Apply and okay. So all right. I just want to make sure that the correlation went across. Let me see this for let me see it in a 2D window. All right, it shows us better in a 2D window. It gives us a better picture in a 2D window. So it covers, look at this is our well TMB 2, and then the last one is probably down here. So it just simply tells us the area that the well is. That's where you have the surface. So that's an easy way of obtaining the surface. Now, What we are going to do now is to build a structural model and to populate property on. So we are going to go to structural modeling. We are going to define our model. We can just call a new model, there's no problem. Once we apply an OK, the new model appears down here. The new model appears down here. These are the various pins here. Ensure that what you have here is model. You click model here, you are going to see it. Oh, I have overclicked it. Oh, there's no problem. So that's our model there. That's our model there. So I'm going to go to simple grid. Simple grid. I will not use a particular, because there are some certain instances where you don't want to be an exact picture of the reservoir with all the undulations and all of that. You may just want to build two flat surfaces and show how you can populate properties in those two flat surfaces. There are so many softwares in the engineering world that is what they do. We have software like the T Navigator, the CMG. That's what they do. You cannot really build this surface where you have the real undulations. So what they will just do is just have some two flat surfaces where you can use to populate properties there. But what we are going to use here is we are going to use a surface, and then we are going to use the surface here. For the top limit, remember that this one was the base and this is the top. This top, I'm going to put it for top. And then this base, I'm going to put it for base to build the model. So I'm going to apply. Oh, not yet, please. I'll come to geometry and I take automatic. I come to geometry and I take automatic. Then I apply. Once I apply, you see how this 3D grid appears here. If I toggle it down, I see so many things on it. If I toggle it down, I see so many things on it. So I see skeleton, I see the horizons and all of that. Our next step now, we will not build this pillar grading. They are very complex grading, that are very complex structures. If you want to go into the real detail of it, you have to go into pillar grading and you build some kind of complex structures where you have to subdivide this this bigger structure into different cells, But we are not going to go into those complex now. So what we are going to do is we are going to take horizons. We take horizons. We want to build a horizon, a horizon from the top to the base, a horizon from the top to the base. So we are going to take our new and new. So we want to build two horizons. This one will be the top horizon. I will put it here. And then this now will be the base horizon. I'm going to put it here. I'm going to put it there. Then I'm going to apply and okay. Once I apply an OK, I think I should be able to see. Now, under the horizons, I have it there. Under the horizon for the models, I have the two horizons. Those are the two horizons. It's just a picture of what we have seen, nothing different. It's just a picture. It's just that you are now transferring it from the surface to a horizon for our model, so that you have to use to build your model. Now, what we want to do is, for static modeling, I think let me just explain a little bit on that. All right. So this is a good picture of what static modeling is all about. For you to build a static model, what you have to first of all do is to build a structural model. A structural model is just a picture of the reservoir. Where does it start and where does it end? Is there any subdivision between them? When I look at the reservoir, when I carry out petrophysical analysis, do I actually see that there is some kind of demarcation? Even if I've considered this as my reservoir, there is something that we call reservoir rock typing. Reservoir rock typing is dividing the reservoir into discrete units that have similar petrophysical properties. So you may realize that within a particular reservoir, it is subdivided into maybe 3 or 4 minor zones there. We have some layers there, 3 or 4 minus layers. So after you have done all of that to subdivide it, that is what we call a structural model. You may now superimpose the fault on the structural model so that it gives us the right displacement of the reservoir, because we may have some kind of displacement also in a reservoir. That one is called fault modeling. We are not going into fault modeling because what we are doing is just a simple static modeling. Because if you want to do just static modeling alone, it should take us about 1 week of at least 3 hours a day. So what we are going to do is at the end of this internship, we are still going to organize subsequent trainings where we may pick some of these aspects now and go detail into it. We are going to pick static and dynamic modeling, and we build these reservoirs, and then you see how you can simulate even dynamic properties to see how fluid will flow from one point to the other. So once you build this structural model, I will not talk more about geometric model. You may want to do some kind of data analysis to see exactly how these properties are. From there now, you may have to build what we call a velogram and all of that. I'll just talk a brief about it. And after that now, you can populate the fasces on top of the structural property, or you populate the petrophysical properties like porosity, permeability, and the net to gross. It is these properties that you will now take, it is this model that you will now take now and try now to do what we call dynamic simulation on it. Once you have built this static modeling, you can now do simulation on it. But if this static modeling is not ready, or if there's a problem with it, then at the end of the day, you have so many difficulties. So there are just some few things that I just want us to mention here. All right. Now what you do is, this is just a picture of what I'm talking about. You may have to build a horizon. A horizon is this top layer and this bottom layer. That is a horizon. That this is my reservoir. My reservoir starts from this horizon and ends at this horizon. For zone now, you may want to subdivide the reservoir into distinct zones, into different zones. Then layering among the zones again, you may still realize that there's still some slight variation again. There's some minor slight variation again within the various zones. So you may now subdivide them into different layers. So if we go back there, so we have done the horizon, which is the top and the base. We now go now to the zone. We now go now to the zone. We may want to add the zone. So what we are going to do now is we are going to just identify them as a single zone. We will just identify them as a single zone. So we see that from here, they talk of stratigraphic interval, R1 top and R1 base. You want to subdivide it. Do you want to subdivide them? If not, then there is no need. If you have seen that there is a possibility to subdivide them, it's still possible for you to subdivide them. But if there is no possibility, we are just going to leave it like that. We will leave it like that. Let me see if isochronal expected zone. Oh. All right, for the zone, for this top, we will just put here R1 there. Okay, surface. So we'll take the surface there. Oh. All right. So what we are going to do is we'll come to this surface, because we have to be sure that the surface is elevation depth. But it's elevation depth, we have to be sure that the surface is in depth domain, not in time domain. Because generally when you picked it on a seismic are usually carried out in time domain. So when you pick a surface in the seismic, you have to do what they call time to depth conversion using you have to do time to depth conversion using your check shot data to convert it from the time domain to the depth domain. Because if it is not in depth domain, everything is going to have a problem. So what we are going to do here is, let me restart it again and see. We don't want any horizon. So we'll just leave it like that. There is no horizon. So we'll go now to layering. We may have different types of layering. Let me see that. We may have different types of layering. Okay. For horizons, there are different types of surfaces that we may have. We have erosional surface, we have the base surface, we have a conformable surface, and a discontinuity. If you look at the base here, what we call a base surface, it has the same dip as the bed. The base has the same dip as the bed. That means before you do this, you must have carried out some field investigation and all of that. If you look at the discontinuity, it starts first of all by having the same dip with the bed. Then along the line now, it becomes an erosional surface. So we have a combination of base and erosional for continuity. When it comes to erosional surface, there is no relationship between this plane, this erosional plane, and the dip of that bed. There is no relationship between them. Then when it comes to layering, there are different ways in which you can layer. You can layer them in a proportional manner. That means they have equal thickness. You can do what we call follow up. If you look at the manner in which the layers are going, that's what they call follow up. It reduces in size as you go up. Then if you have follow top, yours is follow base, this one is follow top. Follow top means it starts from the top, you follow the manner in which the top is, and it reduces down. Follow base means you follow the direction of the base, the dip of the base, you follow the dip of the base, and it reduces up. And then for fraction now, you may want to divide it, maybe in the ratio 1:2:3, or in the ratio 1:2:1, and all of that. So it depends on how you want to do your layering. We will not go detailed into that. So we'll go to layering. We'll go to layering, and we may want to subdivide. All right, so this is our layer. We have just one layer here. The layer is the entire horizon. The layer is the entire horizon, which starts from the reservoir base and the reservoir top right down to the reservoir base. That means if you have picked different reservoirs, you may have all of them here. So what we have is this entire horizon from top to base. How do we want to divide it? Is it in a proportional manner? Is it in a follow base, follow top, follow surface, fraction, or whatsoever? So we want to just leave it probably in a proportional manner. We just leave it in a proportional manner like that, so that it becomes they'll all be equal. So we apply and okay. So once you do that, then I think you come to zone filter, you see the zone here. You see the zone here. So what we want to do now is to go now to property modeling and see how we can carry out petrophysical and Fashi modeling. You have your Fashis here, and then you have the petrophysical modeling there. But the first thing to do is to carry out upscaling. Upscaling is to try to sum out. Remember that we have tried to subdivide this reservoir into different layers. We want to get the average property within a particular area. We want to get the average property within a particular area. Not just because if you don't get this average property within a particular area, there is no way you can actually do this kind of simulation, because it's a mathematical simulation. All of these are mathematical things. If you have done any course like geostatistics, I think you should be having a little bit of idea in things like this. So I will do my Fashi modeling, my Fashi upscaling, I'll do Fashi upscaling. All right, there. What is the average method that you want to use? What is the averaging method? It can be arithmetic mean, it can be geometric mean, it can be harmonic mean, and all of that. But what they use for Fashi is most of. What they use for Fashi is most of. So you just leave this most of like that, then you apply it, and then it's okay. Once you apply it and okay, if you come under properties, you are going to see Fashis. You will see Fashis there. You come under properties, you will see Fashis. All right. Then we go now to the next upscaling. We may have, we take now create new. We don't want to do this. We go to create new. We go to create new. Then you go now to porosity, effective porosity. The averaging method is the arithmetic mean. That's the averaging method, the arithmetic mean. So we just click apply and okay. Then we now go to create new. What other property do we have? Maybe net to gross. For net to gross also, what we are going to use there is the arithmetic mean. We don't have permeability, but if you have permeability, if it is horizontal permeability, you will use harmonic mean. That is the averaging method for horizontal permeability. If it is vertical permeability, you use geometric mean. That's the averaging method for vertical permeability. But since we don't have that, we'll just leave that for now. So we create new, apply, and okay. So you come under these properties, you see your fascies, you see the effective porosity, and then you have the net to gross. We come now to fascies modeling, how to model the fascie. So once you come here, you will see it's upscaled. If you have not upscaled it, you will not see this here. And if this one does not appear, it means that there is nothing else that you can do. So what we are going to do is we click this button that we had here. We will see this lock here. We click it. We see our fascia. What are the various rocks that we want to appear? If you look at it, it's already telling you clearly that within that particular zone, I have clean sand, which is 70 something point this, and then I have shale also with that particular zone, because we already defined our fascies. So you may want to select all of it. You may just select it, select which one you want to display. Select which one you want to display. You select all of it, there's still no problem. You select all of that. Then the next thing now is to do what we call vialogram modeling. This is a very, very huge task in doing static modeling, which I said we are just going to explain briefly because we cannot go detailed into it all of now. So what we are going to do is, let me just give a simple explanation of what the vialogram is. I hope it is on this slide. I just hope it should be there. Upscaling. Okay. All right. So that is a vialogram. A vialogram simply tells us how these parameters are partially distributed in space. Remember that these logs that we have do not occupy the entire area, but we want to populate these properties on the entire area. That means there must be a particular method that is used to predict the property in an unknown area using the values in the known area. So the vialogram now is simply telling us how these properties are distributed in space in 3 dimensions. So we have, for a vialogram, we have the vertical axis. How long is the vertical axis? How long is the minor axis? What is the azimuth and all of that? What is the range? Once you draw, because vialogram, there's a statistical formula that is used to calculate the vialogram value. There's a statistical formula. Once you calculate the vialogram value and you plot the vialogram value against distance, this is how that vialogram value operates. It operates like that. This simply tells us that between this point and this point, there is a good correlation between the 2 points. That means the data that I have that is closest to that point, I can use it to predict the unknown value around that particular point. The distance, the maximum distance where we have that correlation, is what we call the range. Beyond the range, there is no correlation again. Beyond the range, there is no correlation. So I have said this is a whole lot of geostatistical analysis, that if we are organizing maybe a 2 weeks intensive training of at least 2 hours 30 minutes on static and dynamic modeling, we are going to touch all of these geostatistical aspects. But remember, we are just touching a little bit of it now. So we will go back there. So our vialogram value, okay, I cancel that. I cancel that. So we select these logs, the logs that we want to display. This one, even there's nothing there, so there's no need even putting it there. So you realize that here it is telling you, it gives you the measure direction, the minor direction, and the vertical. And here you also have the azimuth. Also. So all of these things are going to be considered. So I am just going to use 15 here, 15,000, because it is what I have done. I have already modeled this variogram before, so we will not go deep into that. Then our azimuth, we are going to take 45 degrees. We'll take 45 degrees for our azimuth. So once you're working with that, just use that. But know that this geostatistics is a whole lot of work to do this. Don't think that you just go to any area and then you just assume this. Then we are going to apply it. Then okay. Then once I come here, I click on Fashi. Oh, hold on. There's an error somewhere. Fashis. Yes, the zone from top to bottom. That's our zone. Yes, the variogram is okay. No. We're supposed to have a good picture of that. Hold on a bit. Once this is clicked, I think we were supposed to have the property. All right, that's it. That's it. So you have to make sure that this zone, that's the zone we have is state, and then we have fasces. So you see how the properties are distributed in space. So you just simply know that if I have my logs, if I come here and I toggle on all my logs, you already know where, if you are to drill these logs, you look at a particular area. So it's telling us that I have sandstone in this particular area, then I have shield in this particular area. I have shield in this particular area. So you may actually know where to drill the next log, the next well. You may know exactly where to drill the next well. So this is what we call a fasci model, to show how the fascies are distributed in space. So we'll take that off. We'll take this also. All right. So we go to petrophysical modeling now to also model. We go to petrophysical modeling to model the properties, the porosity. So we go, the first one is porosity. So we have this also, vilogram value. And then the method of zonation also. There are so many methods of zonation. We have the Gaussian method, we have the crinking method, we have the moving average and functional. Please, there's no way we can go through all of this. Remember that we are just, I am giving you this highlight. If you really want to go into detail of them, go and look at geostatistical method of averaging to see which of this method is used in which case. So what we are going to use here is a crinking. We'll just use the crinking method. We'll use a crinking method. That's what we'll use. And then for this, we'll still use our 15,000. Our 7,000. Then we have our azimuth is going to be 45 degrees, or whatsoever. We can put our 45 degrees here. Then we have, we take it up there. Still not enough. All right, so we take apply and okay. So once we take apply and okay, I think we should come here. We have our horizons. We have our horizon there. That's okay. We have the zone. Then we have Fashi. They're doing the same thing. All right. Hold on, let me see the properties. Exit property. All right, all right. The problem is now the scale. The problem is the scale. So we have to change this scale. We have to change this. All right, we'll use type. We have to change this color. The color does not work. You can come here and you put your legend. Where is that legend even? Show display element. This picture is why you're looking for something. Anyway, let me see how I can change this color. It's not going. That's not what I want. Let me take setting and see if I can get it from there. Colors. All right. So you go to setting, you take color, global color. I will come now here. Oh, no, that's not what. All right. Local, this, make global color. Where are those things? This. All right. I'll toggle it down and I'll take more. I will toggle it down and I will take more. So you have to look at some kind of variation that you need. What are the various variation that you need? Some kind of variation that you need. That's what you're going to look at. If I take, for example, this, I applied, you see how the color will look like now. So when I apply it now, you now see how it changes. But there's still an issue there. You now see how it changes. All right, I think it's okay. That one now is okay. You may want to use this color. No, that one is okay. So, oh, this top palette was still there. So the legend, I think, is somewhere there so that we can see this variation clearly. So that's the porosity model to show us how the porosity varies across that particular area. You may not like the manner in which this one appears. You may not like the manner in which this one appears. You may want to choose another one. You may want to choose another one, maybe this. You apply it, and okay, and all of that. So it depends on you. All of it depends on you. Okay, auto legend, that's what I wanted. All right, so it's giving us a variation in porosity to tell us areas where we have low porosity and areas where you have high porosity. So what I would prefer is that we use this color template. What I'll prefer is we use this color template so that we use limits. We put our maximum value. We know that porosity, the maximum value of porosity is let's say 0.5 because you hardly have a rock with more than 0.5 porosity and the lowest value is 0. So you can always adjust them. You can always adjust them. Maybe we remove this midpoint. All right, so we have this kind of variation so that when you apply it, you see how it is now changing. So it depends on you. You can do some kind of, you can readjust it because I already know that in this particular area, I'm looking at the color. The porosity around this zone is 0.05. So I'm telling myself that this area has very low porosity. But look at this color. It's from 0.25 to 0.2, 0.2 to 0.25. So it's telling me that this particular zone has a very, very high porosity. It's telling me that that particular zone has a very, very high porosity. Then I will also go now to the property model. Also, I do the same. I do the same for net to gross. I take my net to gross. I take the same thing. Let's just repeat the same values that we have. Let's just repeat the same value that we have. And then we have 7,000 there, 7,000 there. And then the azimuth also, let's just put it around 40 something. No problem. We apply and okay. So the net to gross now, I will now click on the net to gross, and it appears the same way because it is still using that same template for volume of shield. So we will now have to go and choose what we want. What we want, the net to gross is from 0 to 1. Is from 0 to 1. I will not like this color, so I will probably choose, oh no, use limit. I will probably choose another color. All right, yeah, so I'll probably choose another color, maybe this. Then down here, I may choose maybe, no, high this way, let's just choose red for that. And then for low area, we may choose maybe that and all of that. So we apply. So you can actually see that in this particular area, there is a very, very low net to gross. So our net to gross is very, very low around this particular area. Around this particular area. Around this particular horizon, but generally in most surface that I've built, we may have portions of high net to gross. And all of this may appear, you may have the wrong modeling. Why? Because you have not done the right, you have not done the right modeling of the vilogram. Once this vilogram modeling is wrong, there is a big problem. Let me take, for example, I change this azimuth angle and I change this to, let's say, 10,000, and I change this to, let's say, 10,000. Once I apply an OK, you realize that immediately you saw a change that took place. There's a big change. There's a change that took place. So once that value, that modeling is wrong, you have a big problem. Once you have a problem here, so that vilogram modeling is very, very important. It's something that can take close to about 3 hours to model the vilogram for each of them. We have used one measurement for all of them, but generally, Fashim model, you model its own vilogram. Porosity modeling, you model its own, and then net to gross modeling, you model its own, and all of that. So all this inaccuracy may arise from the fact that we have just assumed some values for the vilogram and use, but generally you have to model that vilogram. So if you want to learn more on this, you just prepare yourself, because in probably in about three months time, we could organize a course for static and dynamic modeling, where we are going to go from the beginning, from fault picking, how you model the fault, how you pick the horizon, how you superimpose the fault on the horizon, how you use this surface now to model the petrophysical properties, which is the end of static modeling, how you QC the static modeling to be sure that you have done a good job, and then how you now use the static modeling now to do dynamic simulation. And then from there now, you might now export that model. You might export that model even into an Eclipse software. You can do maybe CO2 injection in it. You can do carbon dioxide injection. You can do water flooding and all of that. Just know that before you do carbon dioxide injection, water flooding using maybe Eclipse, you have to do the static modeling. You have to do the static modeling. Most of the time in a company, it's an advantage for you to know all of these things. But most of the time in the company, it is not one person that does all of this. The geologist may be interested in just building the static model. Once the geologists have built the static model and they have QC it and they have seen that everything is okay, they now carry the static model and they give now to the reservoir engineer, and the reservoir engineer start doing whatever they want to do, whatever simulation they want to do with it. But it is an advantage for you to know all of these things. It's an advantage for you to know all of these things. So I think that brings us to the end of our session today. You just go through it and see how. So for all of these structures, all of this, forget about this change that has taken place. This change that have taken place is because of this parameter that I changed down here. It doesn't really matter. You can always change it back. So for all the correlated horizons that you're going to have, Don't pay attention with this upper part. That is the Benin Formation. Mr. Zero already explained yesterday that we don't have reservoirs in the Benin Formation because what they have is fresh water. We have reservoirs in the Abada Formation, so we concentrate around this area. So you are going to pick these horizons, the various horizons, and then you go through the various process of building those models.